Picking up where we left off, we had just re-indexed our two sigmas so that now we can see we actually have x to the k in both. However, notice the counter down below, k equals 0 for our first series, k equals 1 for our second. So tell you what, if we plug in k equals 0 into this first series, we'd get c sub 1, 0 plus 1 is 1. And then 0 plus 1 is just a 1, and then x to the 0 is just a 1, so it's just c sub 1. So picking off that k equals 0 term, just allowing that to be worked in, we can now look at our new series having x to the k in both of them, and even better still, now we'd have k equals 1 down below for both as well. Because of that, we can now take our two series and write them just as one. And tell you what, I'm going to take our coefficients of x sub k and put them together. And you can see what that's going to look like. We have c, and actually this down here is k plus 1, forgive me, c sub k plus 1 times k plus 1, minus 2c sub k minus 1. All of that is what's in front of x to the k. And now, if you're really paying attention, you're going to notice that the left side should equal 0. That leads us to know that c sub 1 equals 0. And what we also have is all of these coefficients here out in front of x sub k are going to have to equal 0 as well. So that means that c sub k plus 1 times k plus 1 minus 2 c sub k minus 1 must equal 0. If not, our left-hand side really won't equal 0. We'll have something with an x to a power on the left side. And this is not saying that our series is a trivial series in the sense of our solution, as if to say, oh, only zeros are going to be seen. Rather, what we're seeing is when we were assuming that y equaled this quantity here, what I've highlighted right here will equal 0. That really will get some terms to cancel each other out if this really is going to solve the differential equation. Well, suffice it to say we're going to be able to get c sub k plus 1. If I'm going to solve for c sub k plus 1 here, I'm going to add a 2 c sub k minus 1 to the right hand side and simultaneously divide by k plus 1. Well, now what we're going to be able to do real quickly is begin to generate our c sub k's. I already know that c sub 1 equals 0 right here, but let's find out what would happen in this generation, in this equation right here, if k were to equal, say, 1. Now, very often kids might say, why not just plug in a 0? Well, then look at this c sub k plus 1. We'd be back at c sub 1. We already know what that is. So I'm going to let k equal 1. That's going to lead us to know what c sub 2 is. Now, when I plug a 1 up in here, 2 times c sub 1 minus 1 is 0. This becomes 2. C sub 0. Plug in k equals 1. This becomes a 2. Real quickly, we can see that c sub 2 equals c sub 0. Well, let's keep going. What would happen if I let k equal 2? Well, c sub k plus 1 would become c sub k sub 3. And then what's going to happen up here? Well, we plug in a 2. 2 minus 1 is a 1. So we'd get 2 c sub 1. all over, well, plugging in k equals 2, 2 plus 1 becomes a 3. Please don't forget, however, that c sub 1 equals 0. We're going to use that information right here and say, okay, that is going to lead us to know that c sub 3 then is going to have to equal 0. What else? Well, we could say, let's take a look at k equals 3. If k equals 3, we'd find c sub 4. And then 2 is up here. K minus 1 would be a 2, so we'd get 2 times c sub 2. Down below with k equals 3, 3 plus 1 is 4. And refer to c sub 2 up on top of our list here. C sub 2 is really c sub 0. So this becomes 2 times c sub 0 all over 4. And another way we can look at that is c sub 0 all over 2. Let's keep going. What happens if we find c sub 4? K equals 4. That means we go to c sub 5. 4 minus 1 is 3, so we'd go 2 times c sub 3. Now if we're really on our toes, we're going to know what's happening immediately. Look, and down below, k plus 1 is going to become a 5. But c sub 3, look in our list up above, that's 0. In fact, what you're going to notice, if you're really going to think about this, we're going to be generating zeros every time we're going to refer back to an odd subscript. When we're going to have a c sub 3 or a c sub 5, you can see where we're going with that. Notice that the subscript of k plus 1 in the original and my boxed up here and c sub k minus 1, they're actually 2 steps apart. If you think about it, it's 2 steps away from k plus 1 to k minus 1. So when I have an odd index down below, like c sub 5, I'm referring back to c sub 3 and so forth. Something to think about. Well, if k equals 5, well, 5 plus 1 is 6, we get c sub 6. And this is going to become 2 times c sub 4. Down below, 5 plus 1 is a 6. So what was c sub 4? Well, we could even break this down a little bit. 2 over 6 is 1/3, and here's c sub 4. But look above, c sub 4 was c sub 0 all over 2. So this becomes c sub 0 all over 3 times 2, or 6. Something to think about there. How about c sub 7? Well, we know what that's going to. That's going to be when k is equal to 6. We know that that's going to 0 like we had just said. Maybe one more just to stretch this out a tad more. K equals 7. If k is equal to 7, take a look up here. 7 plus 1 is 8. We get c sub 8. And then, of course, if k is equal to 7, we get 2 times c sub 6. If k is equal to 7, down here is an 8. This becomes c sub 6 all over 4. But what was c sub 6? C sub 6 is c sub 0 all over 6. So you could write this as 1/4 c sub 6. But c sub 6 is c sub 0 over 6. So this is c sub 0 over 24. Wow, look at that. So now at this point, let's remember what our solution really was looking like. We said that our solution was y equaled sigma for n equals 1 to infinity of c sub n x to the n. And if that's the case, we could real quickly just write this out and say, well, we'd have c sub 0 plus c sub 1 x to the 1 plus c sub 2 x squared plus c sub 3 x cubed, c sub 4 x to the 4th, c sub 5 x to the 5th, c sub 6 x to the 6th, and so on. This is going on forever. In our particular example, though, as you're looking through this, I hope you notice that C sub 1 was 0, C sub 3 was 0, C sub 5 was 0, C sub 7 was 0. You know what we're really seeing? Every odd power of x was wiping out. And you know what? I'm even going to write over here, here's C sub 7x to the 7th, C sub 8x to the 8th. You can see C sub 7x to the 7th is gone. But let's think through this just a little bit. C sub 0, I didn't know what that was necessarily. But let's take a look at C sub 2. C sub 2 is just C sub 0. I'm going to make some of these substitutions in here and see if we can take this a step further. This was C sub 0, but C sub 2, like we just said, look at that, it's just C sub 0. How about what C sub 4 was? C sub 4, you can see up here, was C sub 0 all over 2. So we had C sub 0 all over 2 for our C sub 4. How about C sub 6? Well, C sub 6 was C sub 0 over 6. So we'd get C sub 0 all over 6. Here's x to the 6. How about C sub 8? C sub 8 was C sub 0 all over 24. And something to think about, just helping you out a little bit. This is a solution that we're coming up with. Down below you could say you've got a 1. I'm going to maybe realize, hey, that's actually 1 factorial. Down below we've got a 2. That's of course 2 factorial. If you look at a 6, the neat thing about 6 is it's 3 times 2. That's 3 factorial. 24 is also a very noteworthy number. Take a guess what that is. If you think it's 4 factorial, you are right. Now, right now you might wonder if this thing does look oddly familiar. I hope it does, because let's just recall, and this is what our answer was for y. Might remember not too long ago we said e to the x, the Maclaurin series, was 1 plus x squared all over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial, and so on. Well, you know, you look at this and you can say, wow, I see a 1 factorial, a 2 factorial, a 3 factorial, all that good stuff, and you might wonder if perhaps something is happening here. Notice all my powers here in my solution for y are even, and yet for e to the x they're not. Tell you what, we can say that for this y, my goodness, if we were to notice this was e to the x squared. E to the x squared is going to be our solution, because my goodness, if I were to substitute in x squared everywhere where I saw an x, you would see very quickly that you'd get all those even powers that you're talking about in our solution that we saw up above. So something to think about here. We could have factored that c sub 0 out in front, and this is our series solution. There are other ways to come to that. In fact, we could have used an integrating factor from way earlier in the year. That would have been a much easier solution. In fact, we did that in class together. But I do want to point out that there are many, many more challenging problems where you're going to have to resort to series to be able to solve them. Lots of work here, lots of things that we need to get used to, mostly about re-indexing and just working through that generation of our coefficients. Well, hang in there, and best of luck to you.